Hello, my name is Sean Fitzgibbon, and in this video I'll give you an introduction to the basic principles of diffusion tensor imaging, or DTI. In diffusion tensor imaging, we apply the diffusion tensor model to each voxel in a set of diffusion weighted images. The diffusion tensor model is fit to the data in each voxel and is used to estimate a diffusion tensor for each voxel. So firstly, we have some parameters that we have measured. Sj is our measurement for this voxel for the diffusion gradient J. S0 is the signal from the same voxel in the baseline or B0 image. And then we have a number of known parameters. Bj is the B value of gradient J, which tells us how sensitive that image was to diffusion. And Xj is the direction of the diffusion gradient, which determined in which direction we are sensitive to diffusion. Both the B value and the gradient orientation are things we told the scanner, and hence we know. So the only term in this equation we don't know is D, which is the diffusion tensor we are trying to estimate. A diffusion tensor is simply a 3x3 matrix that gives us information about how easily things diffuse, not just in general, but in different directions. The diffusion tensor is symmetric, which means that even though it has 9 elements, only 6 of them are unique. Therefore, to estimate these 6 elements, we need to have at least 6 different diffusion directions in our images. In practice, you would usually acquire many more than that. And this is what the diffusion tensor looks like in the top right. dxx tells us the diffusion in the x direction, dyy tells us the diffusivity along the y direction, and dzz tells us the diffusivity along the z direction. And on the left, we see that what these values look like if we present them as images. The tensor also has these off-diagonal terms, and the off-diagonals are proportional to the correlations of displacements along these directions. So why do we need a tensor and not just the x, y, and z components? Well, here is a 2D example of free diffusion, and it has diffusivity in the x direction and diffusivity in the y direction. Now here is a 2D example of restricted diffusion. Now the diffusivity in the x direction is exactly the same as in the first example, and the diffusivity in the y direction is also exactly the same. So to distinguish between these two cases, we use the off-diagonal elements of the diffusion tensor. This is a 2D example, so it only has 4 elements, but the same is true for the 3D case as well. And once we have obtained our data, and we have fitted the diffusion tensor, then what we have is a diffusion tensor oriented along the principal direction of the scanner. So we know the diffusivity in the x, y, and z directions of the scanner. But it would be so much more useful if we knew the diffusivity along the axons and the diffusivity across the axon. And the way to calculate this is actually quite easily. We do an eigen decomposition of the tensor. So we can decompose this matrix into a set of eigenvalues and eigenvectors. Lambda 1 is the diffusivity along the direction along which water diffuses most easily, therefore along the principal fiber orientation. Lambda 2 and 3 are the diffusivity perpendicular to the principal fiber orientation. V1 is the eigenvector associated with the eigenvalue lambda 1 and tells you the direction for the eigenvalue. So this first eigenvalue, lambda 1, tells you how easily water diffuses along the preferred or principal diffusion direction, and the first vector tells us what that direction is. And in very anisotropic voxels, this principal diffusion direction aligns very well with the direction of the fiber bundles. Using this information, we can now very easily determine what is isotropic voxel and what is an anisotropic voxel. An isotropic voxel is simply a voxel where all of the eigenvalues are roughly equal, because water molecules can diffuse easily in all directions. An anisotropic voxel is simply a voxel where one of the eigenvalues is larger than the other eigenvalues. And once we start looking around the brain, we can see, for example, in the CSF, we have an isotropic voxel with high diffusivity indicating free diffusion. In grey matter, we have an isotropic voxel with lower diffusivity, indicating that there is some restriction on the diffusion. And in white matter, we have an anisotropic voxel, indicating restricted diffusion with a preferred direction. And once we have the eigenvalues, we can calculate other measures that tell us something about the microstructure. So for example, FA, or fractional anisotropy, is a measure of variance across the eigenvalues, which will get larger as the anisotropy increases. It is scaled to be in the range of 0 to 1, so an FA of 0 means that the diffusion is purely isotropic, and an FA of 1 means that diffusion is purely along one direction and 0 perpendicular to that. You can also look at MD, or mean diffusivity, which is the mean of the eigenvalues. There are also other measures that can be derived, although these are probably the two most common, and they have been used to look at changes in white matter structure in all sorts of diseases and different groups. This is what these maps look like in a healthy brain. The FA map once again illustrates the large anisotropy in the diffusion in the white matter compared with the grey matter, or CSF. On the other hand, in the MD map, the main contrast is between the free diffusion in the CSF versus the far more restricted diffusion in the white and grey matter. Other measures you might come across are the axial and radial diffusivities. The axial diffusivity refers to the diffusion along the preferred direction of diffusion, so that is the first eigenvalue of the diffusion tensor. The radial diffusivity is the average diffusion perpendicular to this, which is computed as the average of the other two eigenvalues. All of these measures have been used to look at changes in white matter structure in all sorts of diseases and different groups. These summary measures can be used to compare the white matter microstructure between groups. Here is an example where the researchers found a decrease of the FA in multiple sclerosis, even in the white matter outside of the lesions common in that disease. They also found an increase in MD. Such a decrease in FA and increase in MD is often associated with tissue breakdown in the white matter. As the tissues degenerate, there are less hindrances to the water, which leads to higher and less anisotropic diffusion. But we must always be careful not to overinterpret our results, as these measures are a simplification of reality and an indirect measure of tissue microstructure. There are numerous changes in microstructure that could lead to similar changes in FA and MD. For example, an increase in FA and a decrease in MD could be caused by cell swelling or by increased cell density. Alternatively, a decrease in FA and an increase in MD could be caused by myelin loss or by cell death. So we just need to be careful how we interpret these measures or these metrics and not to overinterpret what they mean about the microstructure. Another thing that we have to be careful of when looking at FA is crossing fibers. What we see in the circle at the top is an area of very high FA, and the bottom we see an area of very low FA. So you might think that we have some fiber bundles with really strong axonal direction in the top and not so much in the lower image. But what's happening here is that we have crossing fibers. At the top we have fibers running in the left-right direction, whereas at the bottom we have fibers going in many directions and they are crossing. So we still have very strong axonal directions, but they just happen to be crossing, and the diffusion tensor model can't actually model that very well. So if we were to plot the tensors as an ellipsoid, the top tensor would be a nice cigar-shaped prolate tensor with clear directionality, and the lower tensor would be flat or oblate pancake-like diffusion tensor with no clear directionality, even though the fibers in this voxel do have directionality. This inability to model crossing fibers is a well-known limitation of the diffusion tensor. And there are a number of ways in which we can visualize diffusion tensor information. Here we have plotted the diffusion tensor as ellipsoids. You can see from the size and shape of the ellipsoid what the relative diffusivity, anisotropy, and preferred direction of the tensors are in each voxel. We can also plot the principal diffusion direction as vectors, as you can see here. Or we can color code the principal direction of diffusion. Here, red indicates that the principal direction of diffusion is left-right, green back to front, and blue is up and down. As you can see, compared to other imaging modalities, we can get very rich images of the white matter using diffusion tensor imaging. Thank you.